Let's we see what's bronze state and low definition, but we really want to know what electrophiles and nucleophiles are. What are electrophiles and nucleophiles? So I show you in this video bronze state and low definition. Bronze state and low definitions. What does bronze state and low says? Let's have a look. An acid is a proton, and a base is a proton acceptor. An acid is a proton donor, meaning it's a species that gives proton. The base is a proton acceptor. For example, a hypothetical acid H dissociates into HN negative. So it dissociates into HN negative. As you can see here, this is HN. A negative. So an acid, a proton donor, donates proton in water, forming hydroxonium ions, protonated water H3O plus. A base, a proton acceptor, base, a proton acceptor, base, a proton acceptor. What does it do? It removes protons. It removes protons from water, forming hydroxide ions. Deprotonated water EOH. This is deprotonated water OH. Using curved arrows to demonstrate the mechanism by which proton is transferred from hydrochloric acids and the base water. The arrow demonstrates the movement of the electron by the feature of bronze state Lowry reaction is transfer of protons. So in this reaction, you can see bronze state Lowry reaction. What can you see here? You can see this is water and oxygens giving electrons to this proton and forming a bond with this one. The bond would be like this. You can see the bond would be like this. OH bond. This is a bond no formations, and this bond gives plus charge to oxygen. It gives plus charge to this guy. No water has plus charge. Oxygen has a plus charge in water because it has formed now 3 bonds, and chlorine lines which was here. It's chlorine took electron. They say bye bye, I'm going to go, I have an electron here. So this happens here. So we're talking about the topic is we're talking about electrophiles. We're talking about electrophiles and nucleophiles. What are these things? Electrophile and nucleophiles, and this is a definition from bronze state and Lowry definition. So we're talking about first. This is water picking up proton by donating electron from oxygen. Chlorine is leaving, plus water plus. And what else we see here? A lone pair from base creates a new bond with an acidic proton, and the electron pair originally liking the protons to the remaining of the acid shift become a lone pair on the depending conjugate base. So I will explain this one with us. The first thing you say is lone pair from base. So if there is a base and it has a lone pair, what does it do? It creates a new bond. So a base lone pair form a new bond because lone pair there are 2 electrons, they form a bond with an acidic proton which is from the acid. So base forms the proton with form a bond with the proton from the acid from the lone pair using those electrons. And the electron pair originally linking to the proton, and there would be electron which were originally linked to the protons, because proton was bonded to something. It was bonded to acid. So those protons which were originally linking to the protons to the remainder of the acid shift to become a lone pair. So there would be whatever part is left of the acids, those would be electron, and they'll become a lone pair on the departing conjugate base. And the base which is separating, that becomes a lone pair. And that I show you, this is the base separating, these are the acids. So it's just telling that acid has a proton is leaving, but it's not taking electron with it, but those electrons are going on the negative part, and they are becoming the lone pair of that part. Means lone pair is on chlorine, and chlorine has a 2 electron. Now proton goes, says, oh, I don't want your electron. It says both 2 electrons, and chlorine, you see, is just negative. So this was what we're talking about. Whereas the water is a neutral compound, hydrogen ion equal to hydroxyl ion, that thing is called neutral. Where self-dissociation dissociates, equilibrium constant K is self-ionization constant, describes the process at this process 25 degrees centigrade. If you see water, 2 water molecule, Kw is hydronium ion plus OH, but how much the value is, this is Kw. If you want to calculate, it would be like this concentration plus 10 equal to, mean this concentration plus hydroxyl ion concentration, mean AH plus OH, both molar concentration in brackets, and equal to 10 raised to power minus 14 mole scale per liter scale, small scale per liter scales, mole scale per, because the mole per liter, so 2 moles, 2 concentrations, so the small scales per liter scale into the power minus 14 Kw. pH, the negative logarithm of the value of H3O positive, the concentration, the pH is negative logarithm of the value of the H3O concentration. The concentration of H3O in pure water is 10 raised to power minus mole per liter, pH equal to log equal to H3O positive concentration, pH in pure water equal to +7. pH is greater less than 7, then greater than 7 is a basic, and if it is smaller than 7, mean pH less is the acidic. Acidity or general acid, Ha is converted by a general equation, Ha plus water, H3O plus A negative, K equal to H3O plus A negative, and this is Ha and H2O, both things, you multiply these things, H3O in plus into A negative, these 2 things if you multiply, and these things are Ha and H2O. So this is H2O and Ha. So these things goes because you can take this one underneath this. So acidity constants Ka equal to KH2O equal to H3O plus and A negative, both multiplications. So acidity constant Ka equal to K into H2O equal to H3O plus A negative divided by Ha mole per liter. So this is Ha. So if you want acidity concentrated water, you just take this one here. So like H3O can be put to logarithm scales, pK equal to minus log Ka. pK describes the pH of an acid at 50% association. If pK is less than 1 strong, pKa is less than 4 weak acids. Please refer to the chart below. If A derived from the Ha is referred to as a conjugate base, A derived from the Ha is referred to as conjugate base, acid base, conjugate base plus conjugate acids. Conjugate acids and base are inversely related. Strong acid, weak conjugate base, strong base, weak conjugate acid, strong base, weak conjugate acids. HCl strong acid and H plus Cl weak conjugate base. So this is Cl is a weak conjugate base. CH3OH weak acid, H plus CH3O strong conjugate base. So this is acetate as strong. So we're telling you estimate relative acid base strength. What is this? Estimate estimation of relative acid base strength. Relative strength of an acid and weak of conjugate and weakness of a conjugate base can be estimated using 3 structures properties. First things, number 1, electronegativity. Electronegativity and thus acidity increases as we go left to right across the periodic table. Great electronegativity results in more acid solutions, acid protons, and more polar bonds. Molecules gets larger as we go down in the column in the periodic table. This association of large A is favored because the first hydrogens and the larger outer shells overlap is poor, creating a weak HA bonds. This can further explain the electron repulsion, which reduces when outer shell orbitals allow electron to occupy a greater volume of escape. So molecule get larger as we go down. Reduced when outer shell orbitals allow electron to occupy a greater volume of space. So this we're talking about also acid. So acid, they will be less acidic when shells are bigger. Delocalization of a charge into several atoms is accomplished with resonance sulfide. The presence of additional electronegative atoms in A increases the effects. If there is more delocalization, so this will be more acidic. So now we get an example. This is a strong acid. This is a strong acid. As acetic acids, he has CH3C carbon oxygen double bond, 2 lone pair here, 2 electron forming bond here. This is 2 lone pair as well. Other 2 electron, 1 electron oxygen is sharing with the carbon, and other electron with oxygen. What happens when water comes? Water has 2 lone pairs and 2 electrons fused to form a bond with hydrogens. Other electrons. So what happens? These lone pairs, pick up these protons from the strong acids. This is H3 plus what you got from here is just, you won't see proton then, but there would be more electrons, means, because these 2 electrons taken by, so you will see another 2 electrons. This is another lone pair and negative charge. This then provide a push here and here. You will see O double bond here, and this will be O negative again, because this got another 2 electrons, so it will be 2, 2, 4, 2, 6 electron and bond as well. So this is a negative charge, and this is no negative charge because 4 electron. Whenever you put oxygen 6 electron bond as well, you have to put the negative charge. This is weaker bases. This is weaker base. I mean, this is a strong acid, but the base where you got from it is a weaker base. So we're talking about further summary. Basicity of A decreases to the right and down the basic periodic table. Acidity of HA increases the right and the down the periodic table. So basicity influence decreases if you go here towards right and down, but increasing size if you go down, and basicity, you have basicity of the A decreases to the right and the down to the periodic tables of the HA, while acidity of HA increases to the right and down of the periodic table. So if you go right or if you go down, it's more acidic, but the base is opposite. I mean, if you go down, basicity is less. If you go right, basicity is less, but it's more acidic. So just remember one thing. I mean, if you're going towards right, acidity is more. Going towards down, acidity is more, and basicity is opposite. So basicity is basicity of HA decreases to the right and down of the periodic tables. Acidity of HA increases to the right and the down of the periodic tables. So this is a periodic table. Was just saying increase electronegativity this way, and this is increasing size this way, and we're talking about what happened to the acidity and basicity. Several molecules have ability to act as acid or bases under different conditions. Thus, they are amphoteric molecules, water, nitric acid, acetic acids. This is water, this is amphoteric. See more clearly. I got speak more clear, please. So this is acid, it's water, and water donates proton, so is OH now. This is H2O, now donate proton OH and picks up proton H3O plus. This is levous acids and bases interact by sharing an electron pair. So this is levels acid is equal to electron pair acceptor. Levels acid, level base is electron pair donor. So we're talking about another definition, which is levels acid. So this definition was from estimating relative acid base and using the first thing is the Bronsted and Lowry definition. Where we talk about proton, Bronsted and Lowry definition, we talk about proton when we're describing acid and base. We say the acid gives proton, base accepts proton. The Lowry Bronsted and Lowry and Bronsted acid base theory, we say like this, that acid gives protons, Lowry and Bronsted acid base theory. This is electrophiles and nucleophiles. So we're talking about Bronsted and Lowry acid base theory. The topic here is we were talking about electrophile and nucleophile, but first we described what does Bronsted and Lowry definition is of acid and base. So this is acid and base definitions. We give these examples, and other examples we talk about, here estimating relative acid base strength. We said how you can estimate, and we talk about here electronegativity, more the acid is T more, and we told that how the trend is of the electronegativity in the periodic table. This was an example when this is a strong acid, and your base will be the weaker if the acid is strong here, and the vice versa. This is a periodic table. The other thing, several molecules, we say levels acid and base interact by sharing an electron pair. So what's the levels acid and bases interaction? Levels acid is electron pair acceptor, level base is electron pair donor. Levels base share is a lone pair electron with the levels acid. With levels acid is to form an equivalent bond, So thus can be expressed by an arrow moving in the direction of the electron movement. So we're talking about this is an arrow. Arrow is moving here because levels is a lone pair. We're talking about levels acid and base interact by sharing the electron pair. So this is lone pair. This electron pair is being shared with this proton, and you get HOH. Electrophiles and nucleophiles interact through movement of an electron pair. So electrophiles and nucleophiles interact through the movement electron pair process that exhibit very similar characteristics as an acid base reactions are described using same electron pushing arrows. Electrophiles, electron loving and electron deficient atom, which loves electron or ion or a molecule that is affinity for electron pair to accept, and will form bonds one to a base or the nucleophile. All levels acids are electrophiles. 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 Electron-loving species, electron-loving and electron-deficient atom. That's acid. Nucleophile. So we were telling you the definition of electrophile. In the beginning, we didn't tell. We just give you a concept of acid base. But now we're telling you what electrophile are. Electrophile is electron-loving, something that loves electron. An electron-deficient atom, ion, or a molecule that has affinity for an electron. That's affinity for an electron. There is affinity for an electron pair will depend upon the nucleophile. Levels acids are electrophiles. So electrophiles, electron-loving and electron-deficient atom, ion, or molecule that has affinity for an electron pair and will bond to a base or a nucleophile. So it will either bond to a base, an electron-loving species, electron-deficient atom, and either bond to a base or electrophile, i.e. levels acids are electrophiles. It will electrophiles, electron-loving, levic acids are electrophiles. They love electron. Nucleophiles, nucleus-loving, and an atom and a molecule that has an electron pair that may be donated. So it's going to donate electron by bonding to an electrophile. So this is going to bond to electrophile. And the same way, first we said electrophile have electron-loving species, they're going to like to form bond with the electrophile species, and the electrophile species likes to give electron to the nucleophile to form a bond. So this is the reverse, there's the relationship in which, one thing gives electron, other thing accepts electrons. A nucleus-loving species, a love nucleus is a positive charge loving species, and means protons, H plus loving species. So this is, we're talking about nucleophile, nucleus loving, an atom, or molecule that has an electron pair that may be donated in bonding an electron of the Lewis acids. All the nucleophile or Lewis bases, all the nucleophile species with love nucleus, they are Lewis bases, they have electrons, so they can give to a proton, and proton is a nucleus, so they are nucleus lovers, nucleophiles. The diagram below demonstrates the flow of electron using electron pushing arrows. So we are going to show you diagram. This is amazing diagram. You can see this is a base. Base comes. Base loves what? Base is a donates electron. So this is nucleophile. So what is the nucleophile? Is gives electron to this guy, which is a methyl chloride. When methyl chloride is forming bond with chlorine, chlorine is now away, and it is satisfied with forming a bond with the OH, which was a nucleophile. When chlorine leaves, you see this is CH3OH, and chlorine is leaving. You see negative charge here. So this is an example. Now we talk haloalkanes, compounds with carbon halogen bond are generally nucleophilic substitution reaction. Despite differing halogens and arrangement of substituents, all the arrangement combination behave similarly, allowing us to conclude that it is actual presence of carbon halogen bond, halogen that controls the behavior of the haloalkane, The CX bond is a functional group. The CX bond is a functional group controlling factor of reactivities. This is a functional group, controlling factor of reactivities. I think that is sufficient for you today. Means if we review, we talk about here, by giving different examples in this lecture, we have talked about nucleophiles and electrophiles. Electrophiles, we have told you, is electron-loving species, something which has a positive charge like acids. And nucleophile, nucleus-loving species, a species which love nucleus, have the opposite charge from the nucleus. So that is electron-rich species, which has more electrophiles. So nucleophile, nuclear-loving species and rich in electrons. Electrophile, electron-loving species, there will be deficient electrons. Bronson-Lowry definition, which describe you acid is that gives protons. So this is acid, it gives the protons, and other definitions we're talking about electrons. So acid is a species which accepts electrons. So here you can see these electrons are accepted, then proton is being tolerated, because the acception of electron results in the formation of bond with this proton. And the trend is when we go towards right, the more electronegativity and the more acidity, there is more acidic, because more acidic is only that thing which gives protons more easily, and a species gives proton more easily. Which species gives a proton more easily? The species gives protons more easily. So we're talking about acidicity. We say that if you go right, the acidicity increases, they're more acidic, they can easily give protons, because they're pretty electronegative atoms here. So if the more electronegative atoms attached to the protons, they will give easily to electrons, because there is a polarity, and if you go down due to increases size, more polarity, and you can lose the electron more easily, so it's more acidic as well. So increasing electronegativity this way and increasing size this way. In both things, acidity decreases and basicity increases. Lewis acid-base interaction by sharing an electron pair we're talking about. So this is sharing of electron pairs, electron pairs being shared, and you get water here. And this is, you see, base is giving electron to the methyls, and we're talking about here that